Welcome to another session in number theory. In today's session, we are going to categorize the set of all positive integers into three. The first among these categories consists of just one number, which is 1 itself. The second category consists of numbers called prime numbers, and the third category consists of numbers called composite numbers. We are going to discuss how we define these primes, composites, etc., and we will see a few properties of them in addition to seeing a few examples also for them. A positive integer n greater than 1 is a prime. Definition is the following: if it has only two positive divisors, 1 and n itself. So if we have a positive integer n which is greater than 1, we say that it's a prime provided that it has only two possible divisors, and we know that 1 is a divisor of any number and that number itself is a divisor of that number. Therefore 1 and n are the only two divisors, then we call n to be a prime. Example: 2 is a prime because 2 has only two factors, 1 and 2. 3 is a prime because 1 and 3 are the only factors or only divisors of 3. 5 is a prime because the same reason 1 and 5 are the only divisors. Now we have the second definition: a positive integer n greater than 1 is a composite number if it is not a prime number. So composite number basically has no other definition except that it is a number, it is an integer greater than 1, which is not a prime. Therefore, it's some kind of a negative definition in the sense that we say something to be composite if it's greater than 1 and it is not a prime. So what is the definition of prime? We call an integer, a positive integer greater than 1 to be a prime provided that it has exactly two positive divisors, 1 and that number itself. Now, examples for composite numbers, there are plenty. 4, because this is not a prime for the reason that it has divisors 1, 2 and 4. There are three divisors. 6, its divisors are 1, 2, 3 and 6. There are 4. Now 8, 1, 2, 4, 8. There are more divisors than that a prime can actually possess. So we have 2, 3, 5, 7, etc. They are all primes. 4, 6, 8, etc. are all composite numbers. But what about 1? 1 is not a prime. 1 is not a composite. So 1 enjoys the property, or 1 does not enjoy the property of being a prime or being a composite. 1 is just 1. Therefore, we categorize a set of all positive integers into three. Uh, the first set is singleton set 1. Second set is the set of all prime numbers, positive integers greater than 1 having exactly two positive divisors. Third set of numbers is composite numbers, which are positive integers greater than 1 and that are not primes. So we categorized the set of all positive integers into three categories. If you want to look at the set of all primes in the range 1 to 100, probably the Sage math software can be quite useful. And I'm trying to find the set of all primes in the range 1 and 100, and the result is the following. So 2, 3, 5, 7, 11, etc. up to 97. Therefore, 1 is, of course, we have already seen that by the definition itself, 1 is not a prime. We have seen after that that 4 is a prime, sorry, 4 is not a prime, 6 is not a prime, etc. And finally, 97 is a prime, and 98, 99 are not primes. Therefore, we have the set of all primes in the range 1 to 100 consisting of all these numbers 2, 3, 5, 7, etc. This is the set of all primes in the range 1 to 100. As we already mentioned, one is not considered to be a prime or a composite number. One is just considered to be a multiplicative identity, and sometimes we call one to be a unit. So another name for one is that one is not a unit, one is actually the unit in the set of all positive integers. Another important observation probably is that, see, if we try to find out the set of all primes, that means that we have to start from 2, we have to we have to move to 3, we have to then take 5, etc. A probable question is that how many primes we can actually find out. We will be shortly seeing that the set of all primes is not finite, or there are infinitely many primes. We will see that in a short while. Before going to prove that there exists infinitely many primes or the set of all prime numbers is not finite, we will try to establish something that is going to be quite useful for proving the infinitude of primes. So the question that we are going to face is the following. If n is an integer greater than or equal to 2, so that n has a prime factor. Recall that by our definition, n equal to 1 cannot have any prime factor because prime we are starting only with 2, and if something has to divide 1, it has to be less than or equal to 1. If some positive number has to divide 1, it has to be less than or equal to 1, and all the primes are greater than 1. Therefore, definitely 1 cannot have any prime factor. Now, the question we have is to show that if n is a natural number greater than or equal to 2, show that n has a prime factor. In many problems in number theory, including this one, we use induction as a tool, mathematical induction as a tool to establish that what we actually want. So the first step in induction is to show that whatever we are claiming is true for an initial number. Here we have to consider numbers starting from 2, and therefore we have to check if n equal to 2 has the claimed property. That means if n is equal to 2, then can we say that n has a prime factor? So the first case, this is step 1 in induction, n equal to 2. Then what about n? Does n possess a prime factor? Of course, because 2 itself is a prime, and 2 is a factor of n, or 2 is a divisor of n. Therefore, n has a prime factor. And what is that prime factor? 2 itself. Therefore, our claim, what is the claim? So the claim we want to establish is this. This is our claim. N has a prime factor. That claim is true when n is equal to 2. Now, what is the next step in induction? Step 2. You may be aware that there are two types of induction that's being widely used in mathematics for establishing mathematical facts. One type of induction is known as weak mathematical induction, which is most of the times called as mathematical induction. And the other type of induction is known as strong mathematical induction. The strong mathematical induction, the assumption we are going to make will be much stronger than what we usually do in the case of weak mathematical induction. That means in the usual ordinary mathematical induction, which is the weak mathematical induction, the method of proving that something is true is the following. We will prove that whatever we are claiming is true for an initial element. Then we assume that the statement is true for some intermediate element, say for some n equal to k. We will assume that the statement is true using the assumption that for the initial element it is true, and for n is equal to k it's true. We will prove that the statement is true for n is equal to k plus 1 also, and therefore we precisely prove that from n equal to k you can move to n equal to k plus 1. That is a step in induction, inductive step. And in that case, by the induction hypothesis, If you can move from k to k plus 1, and if you have at least one element already established, then the statement is going to be true for every natural number. That is what the weak induction principle says. Now, what about strong induction? In the case of strong induction, the situation is slightly different. In the case of strong induction, what we usually do is, as in the case of ordinary induction, in the beginning we will show that the statement is true for an initial number. For example, suppose that for n equal to 1, we will show that the statement is true. But in the next step coming, it's slightly different. So we will assume that the result is true. Remember that in the weak induction, we will only assume that the result is true for n equal to k, and then we will move to n equal to k plus 1. Here the difference is that in strong induction, you need to assume that the result is true for all numbers up to k. That means the result is true for the initial number, the result is true for the initial number plus 1, the result is true for the initial number plus 2, etc. The result is true for k minus 1, and the result is true for k. That's what here we have to assume. And then we will prove that the result is true for, then we will try to prove that the result is true for n equal to k plus 1. Assuming that it is true for all numbers up to k, we will prove that it's true for k plus 1. But in the case of weak induction, assuming that it is true for n equal to k, we will prove it for n equal to k plus 1. So in the case of strong induction, we actually need a stronger assumption. We actually need to assume that the claim is true for a multitude of numbers instead of assuming it for just one number. Okay, in the case of weak induction, we are assuming that the result is true just for one number. That is precisely the difference between strong induction and weak induction. Here we are going to use strong induction. That means we will assume that up to some k, the claim is true. What is our claim? The claim is that every n greater than or equal to 2 has a prime factor. We will assume that this is true up to k. Up to k means, so if you choose 2, n equal to 2, that we have already proved. If you choose n equal to 3, n equal to 4, etc. up to n equal to k, for every number between 2 and k, we will assume that n has a prime factor. And using this assumption, we will prove that n equal to k plus 1 also has a prime factor. That is a technique that we are going to employ here, strong mathematical induction. So we are going to use strong induction. Assume that n has a prime factor for n equal to 2, etc. up to k. We will now show that n equal to k plus 1 has a prime factor. So we are going to show that n equal to k plus 1 has a prime factor using the fact that if n equal to 2, 3, etc. up to k, then it has definitely a prime factor. So n equal to k plus 1. If k plus 1 itself is a prime, as in the initial case n equal to 2, if k plus 1 itself is a prime, then it has already a prime factor, that is k plus 1 itself. If k plus 1 is a prime, n has prime factor or prime divisor k plus 1 itself. There is nothing to prove. So if k plus 1 is not a prime, then we are supposed to prove that it has a prime factor. So suppose n equal to k plus 1, not a prime. If it is not a prime, remember that we have already assumed that n to be greater than or equal to 2. Therefore, if it's not a prime, it has to be a composite. Therefore, k plus 1 is a composite number. So what is the property of a composite number? So what is the property of prime number? Prime number has the property that it has exactly two divisors, 1 and n itself. So we know that Every divisor of a number, every positive divisor of a positive number must be less than or equal to that number. So k plus 1 is a composite number, means that it has some other factor other than 1 and k plus 1 itself. Therefore, it has a factor k such that 1 less than k less than k plus 1. Because if it has only factors 1 and k plus 1, then k plus 1 is going to be a prime number. But k plus 1 is not a prime number, therefore it has definitely a factor a lying between 1 and k plus 1. And therefore, if a is a factor, then a divides k plus 1. So we can write k plus 1 equal to a into b for some natural number p. But remember that a is between 1 and k plus 1, a is not 1, a is not k plus 1. Therefore, b cannot be equal to 1, because if b is equal to 1, that means that a is equal to b is equal to 1 means a into b is equal to a, therefore a is equal to k plus 1, which is not true. If b is equal to k plus 1, that is also not possible, because if b is equal to k plus 1, a will become equal to 1. That's also not possible. Therefore, b lies between 1 and k plus 1. So A is between 1 and k plus 1, B is also between 1 and k plus 1. So the important observation here is that A is less than k plus 1, but according to our assumption, what is the assumption that we have made? For n equal to 2, 3, etc. up to k. So A is less than or equal to k, B is less than or equal to k, because A is strictly less than k plus 1, that means that A is less than or equal to k, B is also less than or equal to k. Therefore, by assumption, what is the assumption? If n equal to 2, 3, etc. up to k, it has a prime factor, right? It has a prime factor. A has a prime factor, and of course, B also has a prime factor. Now, A has a prime factor. Let B be a prime factor of A. Therefore, P divides A. But what is n? N equal to k plus 1 equal to AB. Now, P divides A implies P divides AB also. That means P divides k plus 1. That is, P is a prime factor of k plus 1. So k plus 1 has a prime factor. So we establish using the fact that every number between 2 and k, the number has a prime factor. Using that fact, we prove that n equal to k plus 1 also will be having a prime factor. Therefore, mathematical induction says that if you are able to establish one statement for an infinite element, if you are able to establish that, the statement true for n equal to k means the statement true for n equal to k plus 1 also, then it's going to be true for all natural numbers. Therefore, we have established that. Therefore, by mathematical induction, every n greater than or equal to 2 has a prime factor. We established it. Now we are going to show that the set of all prime numbers is not a finite set, or otherwise, in the set of all natural numbers beginning with 2, there are infinitely many prime numbers. We are going to follow the proof given by the famous mathematician Euclid in his classic text called Elements. So we are going to prove that the set of all prime numbers is not a finite set. So the statement that we want to make is precisely the following. This theorem is attributed to Euclid, even though probably it's most probable that he himself has not provided the proof, but he just kept this proof, this particular proof, in his book called Elements. But since we are finding this proof for the first time, probably in his Elements, and therefore most of the times this proof is attributed to mathematician Euclid. Statement is the following: there are infinitely many primes, or the set of all primes is not finite. To prove this, we will initially consider a set of primes which is actually finite. Let P1, P2, etc. Pn be primes. So we are considering n primes, and this we can using these primes we can actually form a set. Set is set of P1, P2, etc. to Pn. This is definitely a finite set because we are considering only n prime numbers. Now we are going to show that whatever finitely many primes, whatever set of finitely many primes we take, we can always find a prime that is outside this set. Means we can find a prime that is not in the set of primes we have taken. That is what we are going to show. Write n equal to p1 into p2 into etc. into pn. So take this product and add 1 to it. So n is the product of all primes plus 1. Okay, we are constructing a new number. So does P1 divide n? That's the first question that we want to ask. Does P1 divide n? That is the first question. You can actually observe a small problem if this happens. Suppose P1 divides n. Suppose P1 divides n. So if P1 divides n, we know that P1 divides, we know that P1 divides the product P1 into P2 into etc. Pn, because P1 is already here, that's a factor of the product P1 into P2 into etc. Pn. Therefore, P1 divides n by our assumption. This is the assumption. And this is non. So this is the assumption and this is not. Therefore, P1 divides n, suppose we are assuming so. Now P1 divides the product P1, P2, etc. Pn. Now we have already seen that this is non. That if A divides B and A divides C, then A divides B plus C, A divides B minus C, both these things we know. Here we have P1 divides n, P1 divides the product P1, P2, etc. up to Pn. Therefore, P1 divides their difference also, that is n minus P1, P2, etc. Pn. But what is this n minus P1, P2, etc. Pn? We know that n is equal to P1, P2, etc. Pn, the product plus 1. So this is going to be equal to 1. Therefore, P1 divides 1. But P1 is a natural number that's greater than or equal to 2. But P1 is greater than or equal to 2. And every divisor of a positive number, every positive divisor of a number has to be less than or equal to that number. Therefore, P1 dividing 1 is not possible. Therefore, since divisor of 1, positive divisor, is 1 only, this is not possible. What is not possible? P1 dividing 1 is not possible. Therefore, P1 dividing 1 is not possible means that P1 dividing n minus P1, P2, etc. Pn is not possible. But clearly we know that P1 divides. This is non. P1 divides P1 into etc. Pn. And therefore, what has to be wrong? P1 dividing n, our assumption must be wrong. Therefore, the assumption that our assumption is wrong. So what is our assumption? Our assumption is that P1 divides N. This has to be wrong. This is not correct. So P1 cannot divide N, or Pn does not divide N, or P1 cannot divide N. So P1 cannot divide N. Similarly, we can show that P2 does not divide N, etc. Pn does not divide N. So we have taken a finite set of prime numbers, P1, P2, etc. up to Pn. We know that N, we know that N is greater than or equal to 2 because N consists of primes and each and every prime is greater than or equal to 2. Therefore, N is greater than or equal to 2. Therefore, N must have a prime factor because we have already proved that any integer greater than or equal to 2 will have a prime factor. So, N must have a prime factor, but its prime factors are none of P1, P2, etc., Pn. Therefore, it must have a prime factor, but they are none of P1, P2, etc. up to Pn. Therefore, that means that n has a prime factor different from P1, P2, etc. up to Pn. Therefore, there exists at least one more prime because we want n to have a prime factor that is not P1 or P2 or etc. Pn. Therefore, there exists at least one more prime number other than P1, etc. Pn. So the moral is the following. Suppose that we are taking a set of finitely many primes or a finite set of prime numbers. From that finite set of prime numbers, we can always arrive at the conclusion that there exists one more. Suppose that we take 100 primes, we will say that there exists one more. So at least 101 is there. Suppose that we take 101 primes, we say that there exists one more. That means 102 primes must be there. So if we keep on going like that, whatever finite set we take, we will keep on saying that there exists one more, and therefore it becomes true that we cannot stop with any finite set of prime numbers. Therefore, there exists a prime outside any finite set of primes. So any finite set of primes, that means that there is no fixed number of elements in that finite set, so that we can definitely say that this is actually the set of all primes. Any finite set will exclude at least one prime. So finite sets are not enough to contain all the prime numbers. Therefore, primes there are therefore primes are infinite because no finite set can contain all the primes. Therefore, primes must be infinite, establishing what we stated as the Euclid's theorem. There exist infinitely many primes. We will see a small example to demonstrate what we have proved here. That is, we will take a few prime numbers. For example, we can take the first few prime numbers, and we will show that there exists at least one more outside what we have already taken. Suppose that we consider all primes in the range 1 to 20. Therefore, the primes are so uh, primes in the range 20. Suppose that we are going to generate it like this: prime range 1 to 20. And if we ask what are they, we will get something like this. These are all the prime numbers in the range 1 to 20. So what is our n? N equal to the product of all elements in this prime 20 set. That means you have to take the product of 2, 3, 5, 7, 11, etc. up to 19. So this is equal to product of all the elements in the set primes 20, and now we have to add 1 to that. And what is this n? This n is now nothing but, so we get it to be a somewhat a large number, and we are getting it to be 969,969,1. Very good. We are getting such a huge number. And now we know only these primes. 2 we know, 3 we know, 5 we know, 7, 11, 13, 17, 19. We will try to see what are the factors of, what are the prime factors of this 96, what is this, 969,969,1. Okay, we will try to see what are the factors of it, or prime divisors of it. Prime divisors of this number. So we get the prime divisors of this number to be 347 and 27953, and 347 is not in the first set of the set of primes we have taken. 27953 is also not in the set we have taken. Therefore, it has prime factors different from what we have already taken. So this is a kind of demonstration to see that what exactly we have done. So I hope that you understood the proof and the example that we just demonstrated using Sage Math software. And we will continue with the properties of primes and composites in the next session also. Thank you.